Welcome to our next seminar where we have my friend Petar Paves speaking on singularity-free motion planning for redundant parallel manipulators. So please, Petar, the stage is yours. Please start.
Okay, so thank you very much for this exhaustive introduction, and thank you to the organizer for this kind invitation to talk at the seminar. Just a few things before I start. I'm going to full screen mode, which means that I won't see raised hands and things like that. So please, if anyone has any questions, just say something, and then I will try to react. And also, I will I will make a break or two for you if you want to ask questions or explanations and things like that. Okay, so now I'm in full screen mode, and let me start with my talk. So it's about singularity-free motion planning. So first, just a brief introduction and explanation of what I'm going to talk about. I will try to convey the main ideas and avoid most of technicalities. Most of the things that I will say will be mathematically correct, or at least correct under some assumptions, which are sometimes technical. So I mean, please keep that in mind. Usually, I assume that something is generic or most of the time true, and some things like that. Okay. Anyway, so. I think that most of you know what is motion planning, but just in case, that's essentially one of the basic tasks in robotics. It's called in different ways. It's path planning, navigation problem. Popularly is known as piano movers problem. And essentially, you have some machines, usually some robotic device or something similar, and it requires a planning to find a path between two configurations, like which avoids obstacles, which stay within some boundaries, and I mean this kind of problem. So you are given an initial position or a state of the machine. You are given some final, a prescribed positional state, and then you want to move from one to the other. So the idea is, for example, you have something, you have some room, maybe it has some obstacles. There are a couple of obstacles. Then your machine is here, you want to bring it here, and then the question is, okay, find the path from one point to the other and avoid obstacles, minimize maybe energy, and so on. Now, of course, I mean, this is so basic. That's a huge area of research. There are an infinity of different algorithms, approaches. I mean, minimize energy, use convex geometry, and I mean, there are books and volumes written about this. Now, one special type of this problem is the so-called multi-query planners. Because most of the time, this motion planning is done one set of input data at a time. So, I mean, you have your machine, it has some initial position, some prescribed position, and then you compute a path. But sometimes you want to do some kind of a pre-processing where you have some fixed environment in which you want to move, and then you try to compute in advance a lot, maybe all possible paths. So given all possible pairs of initial and final points, you want to compute the necessary paths in advance. Okay, so this is something that often appears, and it's called many queries or multi-query planners. Okay. Now, usually you do this in some discrete setting, so you have some grid, maybe some graph, and then you get some list of possible solutions, of possible paths. But if your ambient, your environment is continuous, then you essentially get some space with some topology, and then it makes sense of talking about continuity. So around about 20 years ago, maybe a bit more, Michael Farber started to consider such planners and add an additional requirement that those output paths, so I mean, given initial and a final port, so the output paths are continuously dependent on this input data, so the initial and the final point. And of course, this is kind of important because this is about predictability of your paths. And one of the basic things that he proved that in general you cannot obtain continuity on the entire set. So you must split the set of input data into subsets which are in some sense optimal, maximal, and the number of these subsets essentially depends on the geometry of the operation space. Actually, it is homotopy type, but I'm going to talk about this a bit later. Fine. Now, it turned out that this was an extremely fruitful idea. It developed in a nice and theory. There are a lot of people working on that, and the entire area is usually called topological complexity, because topological complexity is just the number of those subsets into which you split the set of all possible inputs. And there are many strains within this theory. So one of them is a computation of topological complexity, and from some initial relatively simple methods, it's becoming more and more sophisticated methods. So you have complicated situations, and then sometimes very advanced methods of computation of topological complexity. So it goes into hard problems in homotopy theory. Then a big part of this subject of this topic is to find connections with other areas of mathematics. It has connections with differential topology, with geodetics, then with algebra when you compute topological complexity of groups. So there are many articles, many papers treating these things. And then maybe something which is closer to this initial motivation is to find different applications of this topological complexity concepts, or of this continuous motion planning, to actual problems in robotics. And today's talk will be about this last type of problems. I'm going to discuss how to define, and then a little bit about how to compute topological complexity for some special type of mechanical devices. So this essentially comes from some recent collaboration with Edward Haug and Adrian Pedro, who study from the, if you want, engineering viewpoint, various singularities of machines, mechanisms which are parallel. And I'm going to explain exactly what it is, and they can be of two types, redundant or non-redundant. And here the emphasis is the theory, I mean development of different methods, essentially kinematics and then dynamics, which completely avoids singular configurations, because I'm going to explain what kind of singularities appears in these mechanisms, and this makes all kind of standard methods difficult or unstable. So the idea is to consider only the non-singular part, the singularity-free part of the problem. So, I mean, my main topic today will be just the formulation. So how to formulate precisely the question, the problem of continuous motion planning in the space of non-singular configurations, and in particular for the special case of redundant parallel mechanisms. Okay. Let me just start again. I think that most of you know a little bit, at least a little bit, about topological motion planning and complexity and manipulation planning, but still let me introduce just some main notation and terminology. So first of all, let me denote by this W the workspace of all positions of a robot device. And this can be just positions, or it may include also orientation of a robot, whatever it is, whatever is important for the activity, for the functioning of the robot. And now the problem is the following: you are given two points, two states within this workspace, and you want to find a continuous path which corresponds, of course, to a motion. And let me call it alpha of these two, initial and the final point, and the path which runs within the workspace, so within, in a sense, allowable positions of the robot. So this path should start at the first point, at W, and at the point W prime. Okay? So that's just the classical formulation of the motion planning. Now we add another requirement, so that the map which maps this pair of input data into a path is continuous, or at least, if it is not, I mean, if you cannot find a continuous solution, at least a solution which is continuous as much as possible. And we call those paths in different ways, of course, continuous, but sometimes we say that is a robust path, or that is a predictable motion planning. And you can imagine this is kind of an essential question whenever you have several objects, several robots moving around. You think, if you walk in the crowd, then someone walks toward you, and then somehow automatically, usually we turn right, and if the other person turns right, then you don't run into one into other, or I mean, you can walk on a narrow path in dense traffic. You have several machines going around, you don't want them to collide, and so I mean, if you want to do this, you must somehow be able to not only plan your own path, but somehow to react on the possibilities of the other side, and this should be somehow predictable, and predictable in a continuous way. It means that, okay, if you detect its position as W and W prime, but then if you are not sufficiently precise with your measurements, so if you get some, measurement which is just approximation of what is the assessment of the other actor or person or robot, then still you should guess with sufficient probability, with sufficient certainty, what's going to be its path, and then you can arrange for this. So this is continuity, is predictability essentially. Okay, and then the minimal number of those predictable motion plans which are needed to cover all possible input, so initial position, final position pairs, is called the topological complexity of motion planning, of navigation planning within space W. And this is exactly precisely the initial definition which was given by Michael Farber in his seminal paper from 2003. It's called topological complexity of motion planning, and which started the entire activity, the entire theory. Okay. So, I mean, during this last 2 decades, there were many important examples, many important extensions. I'm going to mention two. One of them is if you want to move at the same time several robot devices without collisions, of course, then this is essentially talking about topological complexity, not in the space W, but in this configuration space of n non-colliding objects within this workspace. Then another thing is if you want to plan motion, but you have a number of prescribed checkpoints, or I mean things, intermediate points, this is called higher topological complexity. And again, the theory is developed, which allows us to compute either precisely or with some probability these values, so the minimal the minimal number of points. And of course, it's clear that this is important because this kind of measures the problem. What you want to know from the engineering viewpoint is how many different algorithms, if you want, how many different if clauses you need to put in your algorithm. And you don't care if it is 3 or 4 or 5, you care if it is tens or hundreds, and each of those essentially increase with n. So you don't want too many rules, because then your motion plannings become quite complicated. Okay, so I mean, one of the things here is that in motion planning, in this Farber sense, each device is essentially treated as a black box. So, I mean, you just prescribe the initial and the final point. You don't really care how the machine actually moves from one point to the other. So somehow you give it instructions and the machine follows the instructions, and how it performs this task, it's not part of your consideration. A next step is if you kind of open that box, and then you see that there is a mechanism, and the motion of individual parts just then move your machine. So if you are doing actual programming, motion planning, if you want manipulation planning, then you need to take this into account. And it turns out that this is kind of not linear, so this makes the problem, it gives to the problem some additional level of difficulty. It becomes more complicated. So let us first see how this is formulated, how this is stated. So this is something that I call manipulation planning, and now you have two spaces. One of them is kind of the inner space of the robot. So it's a space of parts configurations, since it is usually consists of different joints, either rotational joints or sliding joints. It's called the space of joints, or a joint space. And then you have the space within the robot move, and this is called the workspace, or space within where there is some activity. And those are connected by a map, which is called the kinematic map, or sometimes for precision forward kinematic map, which translate configurations of the inner parts into the position of the robot. So I mean, some things rotate, there are wheels, joints, bars, and things. And in practice, there are not many possibilities, so configuration space is usually a subspace of some product of circles which correspond to to revolute joints, and then is a subspace of some product of intervals or Euclidean lines, which correspond to sliding joints. And also the workspace is usually a subspace. Okay, you can move in a plane, then it is a subspace maybe of the plane, or a plane plus orientation, or a subspace of three-dimensional space, or maybe a subspace of a three-dimensional space together with the orientation of the object. And so elements here are often called poses, which means positions and orientations. So typically C is a subspace of such a space, W is a subspace of some of those, and the kinematic map is almost always just some smooth map. Smooth, but with possible singularities, which means the points where Jacobian has not the maximal rank. Now there are, I mean, a lot of different designs. For example, there are some pictures of the so-called Scara design, or I mean, this is essentially you have two parallel joints and then some sliding joint. This thing goes up and down. You can see the configuration space is S1 corresponding to this joint, cross S1 corresponding to this joint, and then cross interval of if you want reals corresponding to the sliding joint. And the workspace is essentially this gray area, which is just a thickened circle. So it's S1 cross interval cross interval, and it's very easy to write the kinematic map just by some simple trigonometry. It's a smooth map. It is 2 to 1, except on the boundary. So on the boundary you have some singularities. Then there are other examples. For example, this picture, this schematical for the so-called triple row wrists. Again, there are engineering realization of this, and again, it's a map from now you have 3 rotational joints, and it maps, if you want, only to rotations. So you have a map like this. And now the manipulation problem is stated as follows. So here, when you start, your machine is some internal state, C, and you want to move it to some position in the space. So you, to this initial state, it corresponds some initial position, and you want to get to some final position. So if you want to picture this in some way, the picture is like this. So your space of configurations, you can think, I don't know, like you have configurations, some space. This one is mapped into a space of, into a workspace. Maybe there are some obstacles. And now your device is in some state, which corresponds to, of course, to some position in the workspace, and you want to get here. So your initial data is given by initial state and the final position, which means you need to find a path within the space of, within the inner space of the robot or your mechanical device, which eventually, so in the end, brings your robot here. So essentially, you need to find a position in the configuration space which corresponds to this point, and then a path to any point in this this fiber. And of course, if you fix a point, then this is just a motion planning within C. But if you allow any point within this fiber, and fibers can be quite big, then you get an easier and more realistic problem. And again, you insist that the solution that you find is continuous, so you get some predictability in manipulation plans, and you want to define, to consider what's the minimal number of those that are needed, right? So this was like done first by myself. There was a paper in 2017. It's called The Complexity of the Forward Kinematic Map. And then now there are quite a few papers studying topological complexity of a map, which is sometimes assumed to be fibration or not a fibration, or it has some special properties. Okay, so maybe now this is a moment maybe to do just some short break and ask if there are any questions so far. Okay, so either my micro is muted or there are no questions, so I think I can continue. Fine. Okay, one important feature which happens, so if you have this standard situation, so your space of joints is a product of some circles and intervals, and if your workspace is position and orientation. Now, these two spaces are different, fundamentally different. So from the mathematical viewpoint, it's relatively easy to see that they cannot be a fibration. Essentially, the reason is that a fibration should be, I mean, if you can compute homology or cohomology of a fiber, and you see that it should be infinite dimensional. Just play a little bit with spectral sequences. And since everything is finitely dimensional here, that cannot happen. So this map cannot be a fibration. Since it is smooth, this essentially means that there must be singularities, there might be singular points where the Jacobian is rank deficient. And typically this means that at those points your mechanism cannot move in all directions. It's said that it loses degrees of freedom. And one of the important problems or consequences of this is that topological complexity of a map, unless a map is a fibration, but usually it is not, is invariant only to some restricted kind of homotopies and not to all homotopies. So while the topological complexity of a single space is completely a homotopy invariant and it belongs to homotopy theory, here it is not only homotopy theory, it is partly homotopy theory and in part other things, either some singularity theory or some ad hoc computations which help you treat the singularities of the kinematic map. Now, well, it turns out that you can move through singularities or you can try to avoid singularities. Okay? There are reasons to do that because singularities usually mean some unpleasant things in mechanics. So it can mean loss of mobility, like here, or it can mean loss of control. It can mean infinite accelerations, so unacceptable forces that act on the mechanism. So things that you can consider mathematically, but you really try to avoid if you are, I mean, engineering a robot, a mechanical device. And from the computational viewpoint, if you have singularities, then around those it is difficult to state and solve differential equations of motion, which is basically your problem, especially when you study the dynamics of a machine. The problem is that singularities may separate the configuration space. Actually, this happens almost always if you have a non-redundant machine. So this problem cannot be avoided in general because sometimes your path must pass through singular configurations, and that's a problem. Okay. This was essentially studied in the paper that I mentioned before and in some later papers. But from the beginning, there was a question, this forward kinematic map is something that you have, you can compute if you have a so-called serial machine. So you have a sequence of parts which are connected by joints, but they are kind of an open chain. This approach doesn't work very well if you have several chains which are connected. And these, so such mechanisms are called parallel mechanisms or parallel manipulators. So like here, so this is one of the most famous one, is the so-called Stewart platform. So you have some sliding joints, and they are, by moving those, this platform moves. It's very precise, very strong. You can do all kinds of this, and it's used in many different situations in robotics. So the point here is that you have a lot of joints. The space of joints, the possible space of joints is big, but the actual space, because of all those connections, is just a six-dimensional subspace of some really high-dimensional space. So depending on how do you consider those joints, can be like 30-dimensional space, and you have some six-dimensional subspace, which can be essentially anything. Usually, it is very difficult to describe forward kinematics, and often, not always, but often, it is relatively simple to compute inverse kinematics, which means if I say the position and the orientation of this, so the position and the orientation of this platform is something, it is easy to compute length of those legs. I mean, that here it is really an easy exercise, and you can write down the formulas, which means if I prescribe a position, I can easily say, well, how long must be those legs to achieve this position. So you have inverse kinematics and really difficult forward kinematics. Okay, so this is about parallel manipulators. Now, a typical way to model this in a mathematical way is to say, okay, I have some input data, let it call some vector of x's, and then I have some output data, so x is from the joint space, y is from the workspace, and I have some relations, some smooth relations, which is defined as a sequence, a system of equations. Here, this map is usually assumed to be smooth. X is a subspace of the joint space. Y is some space of positions or positions and orientations. And usually you assume that the number of the dimension of input data is bigger or equal than the dimension of the output data. And this mechanism is called non-redundant if you have equality, or redundant if you have inequality. So here it means that essentially for every point in the workspace, there corresponds a discrete set, so one or several points in the joint space, and while here there corresponds an entire, usually submanifold of possibilities within, so you can move within this submanifold of the possibilities. So usually we assume that 0 is here a regular value, so the set of configuration of such a machine, so the set of possible positions is or states is a closed manifold. And here there is one important point. This closed manifold can be disconnected, and actually it is often disconnected, and components of it are called assembly components, which means your mechanism can assume different positions, but some of the positions cannot be continuously transformed one from the other. You need disassemble, to dismount your machine, and then you assemble it in some different way and obtain different positions. Okay? And now, within this space of configurations, there can be many different kinds of singularities. So, and singularities essentially depends on the points where either differentiation with respect to the input data, which is some matrix, or differentiation with respect to the output data, which is again some matrix, if those matrices are rank deficient, they don't have a maximal rank. Okay, so now this is getting a little bit involved and complicating, so I'm going to continue from this point on with some simple example. Probably the simplest possible, which is on one side can be visualized, and on the other hand, it has almost all features as a general case. So mechanism is as follows, really simple. It is constructed from 3 bars. This is the base point, so this one is fixed. There are different. I need for computation to fix lengths. Of course, lengths can be different. This is kind of a generic case. Now, this is a rotational joint. This is a rotational joint. Third rotational joint, and this is a sliding joint. So this point, this is the final point, can just move along this axis. So it's there's some cranking mechanism with a sliding end point. So cranking slide mechanism. So your input data are those X and Y. Your output is a position on the line. So this is Z. And of course, it's immediate how to write this equation. It's just this Pythagorean formula. Inputs are from the product of 2 circles, or we can consider it locally as a product from 2 real lines, and the output is a real or an interval. And since we have 2 input angles and 1 output, this mechanism is 2 to 1. I mean, it's redundant. So the dimension of the input space is bigger than the dimension of the output space. Okay, can we visualize this? Yes, this case is sufficiently simple that we can just draw the solution set of this equation f of x, y, z is equal to 0, and you get something like this. Of course, you must take into account that this is a Cartesian picture. There are identifications, so those opposite circles, if you want, are identified. So you have 1 hole, and then by identifying the opposite sides, you get another hole and another hole here. So the configuration space of this extremely, maybe most basic mechanism is actually already a topologically interesting object, is a genus 3 torus. Okay. Now, this configuration, so we can think of this. So this mechanism moving, this mechanism is essentially walking around a genus 3 torus. That's already kind of interesting to visualize. Fine, but moving around this 3-dimensional, genus 3 torus, we get different singular positions. And they are of 2 kinds. So first are positions where the derivative with respect to the output coordinate is 0, because this is 1 by 1 matrix. And if you compute those points and see to which positions it corresponds, you find out that the derivative with respect to the output coordinate is 0 when this last bar is vertical. And now you can feel, so what you see is if you move just the first 2 joints, you cannot force the bar to go left and or right. Actually, in practice, if you put some force on those, it will just randomly go left or right. So what happens in the position where the derivative with respect to the output coordinate is 0 is that you cannot control your device. You get some loss of control which corresponds to this. Of course, this is, very problematic. You don't want to pass through positions where you are not sure whether your mechanism or your robot is going to move left or right independently on what you do. Okay, so this is first type of singularities. And the problem here is that this set of singular points is usually of codimension 1. So in this case, this is one-dimensional thing, and it splits this torus into the upper half and the lower half. Okay, so that's already a problem, because this means that to pass from the lower part to the upper part, you must pass through singularities when you lose control, and you want to avoid this, remember. Okay, the second type is also problematic, but a little bit more benign. So if you look at the singularities with respect to the input data, you find that, it's a solution of this system of two equations, and you find those 4 on the upper half, and symmetrically there are another 4 singularities on the lower half, and these are the cases when they are horizontal. So what happens here is that you can move, but not in all directions. So you can control your end effector, but for example here you cannot move it to the right, because there is no physically possibility to move it to the right, and similarly in the other positions. So you have a discrete set of 8 points, 4 on the upper half and 4 on the lower half here. Now, you want absolutely to avoid loss of control, and you are keen to avoid the loss of mobility as well. So if you consider the space of the subspace of configurations without, which is non-singular, you get something like this. So it splits into parts, the upper part and the lower part, and on the upper part, together with the identifications, there are 4 points which are cut out. So this is essentially geometrical representation of the singularity-free configuration space, and I'm going to call this C with CF as an additional description. And so each part of it is a assembly. So the upper part is a torus with 2 holes, and the lower part is a torus with 2 holes, and then with additional 4 singularities of this loss of mobility kind. And I can also visualize the kinematic map because this is one-dimensional thing, and is a kind of a Morse map which is depicted like here. So you have this torus with 2 holes, and this is essentially just projection. And what you see is that some fibers are circles, some fibers are pairs of circles, and the singular fibers are unions of 2 intervals. So this is something that we should remember. And now finally, the topological complexity of singularity-free motion planning is just by definition the topological complexity of this kinematic map. Fine, so this is maybe a moment to stop for a second time and check if there are any questions. Okay, so let me continue. Fine, so now I did one example, but so let me generalize this. As I said, this example is, not completely, but quite generic. So most of it will generalize to the general case. So first of all, as I said, I define the configuration space of a parallel mechanism just as a set of solutions of some implicit equation. F of xy is 0, x is input data, y is output data. Sometimes you will see some generalized coordinates which can be expressed using x and y, but I'm satisfied with this situation. And then this is an equation that defines the configuration space of a parallel mechanism, and this one can be redundant if dimension of input data is bigger than dimension of output data. And then I define the singularity-free configuration space as a subspace of this C, consisting of points where the two matrices, so the derivative of f with respect to the input data and to the output data, have maximal rank. And then in addition, I denote by J and call joint space and workspace respectively the projections on the first and the second component. So the set of x's that come from this singularity-free configuration space is called J, and the set of y's is called the workspace and denoted W. And as I mentioned before, it often, almost always happens that this entire space is disconnected. So here I consider one component at a time. So I mean, I take one component and work within this one component because I do not allow moving through singularities. So which means that I stay within the same component. Okay. Another thing which is almost always the case in the practical examples is that the projection of this component onto the J space is injective. So every position of joints which is allowable determines a unique configuration of the space. When this is true, of course, I can define the inverse map from J to C to this singularity-free configuration space. So the forward kinematic map, the map that I'm interested in, is it is the equivalent if I consider a map from J to the space W, or from the entire C singularity-free configuration space. The second one is easier to describe and to visualize. So I define the topological complexity to be the topological complexity now here of this projection map. So it's nicer and easier to describe. Okay. Now I return to what I explained before. The motion planning is essentially splitting the set of all input data, which is configuration space, cross the workspace, so initial positions and prescribed position of the machine, which should give us an output paths in the space of positions of configuration of the robot. And by definition, the topological complexity of the singularity-free motion planning is just the minimal number k, such that the domain can be split into k sets, and such that motion planning is continuous on each of it. And most of the time there is no continuous solution on the entire space, so you may consider the space. So this is some number. You can also study the set of points where this thing is discontinuous. Usually these are called instabilities of alpha, because this just means that there are points where your motion planning, your prescribed behavior is unpredictable. I mean, it can happen that you go left, or you can go and then just some little bit, in a similar position, then you go right or left, or up or down, which can result in a collision if you just move according to your predictions. Okay, so this was the main part of my talk. So how to model the topological complexity problem and motion planning problem for singularity-free motion planning. Now, of course, now that the thing is defined, I can use the previously developed theory to do some computations. So in this final couple of minutes, I'm going to give you a sample of theorems that can be proved in this context. So one of those is interesting. I didn't consider this previously, and it was a nice thing. So the question is, you take some motion planning. It must be discontinuous most of the time. So the question is, if you look at some specific algorithm, how many points of discontinuity can be there? So Michael Farber, in some of the first paper, considered the degree of instability. So how many different choices you can have around some point. But this question is different. This question is about what is the size of the set of instabilities. And it turns out that it must be quite big. So I was able to prove this theorem. So first of all, assumption is that for some position in the workspace, the fiber, so the set of all positions which correspond to this W0, contracts to a point within the singularity-free configuration space. If this is the case, so if you have at least one fiber, which is what we call usually categorical within the configuration space, then whenever you find a subset of the configuration space which is not categorical, there must be a point in this subset such that the pair, so the task to move from C to W0 is a point of instability for alpha. So this is some kind of Lusternig-Schneiderman theorem. If you look at it, at each subspace of which is not categorical, there must be at least one point of instability. So let me show you what is the case. What does it mean here? So I mean, those red lines, those are the fibers, and you see that at least the singular fibers. So for example, this one is a union of two. I mean, because I eliminated this point, I cut out the singularity. So this fiber here is can be deformed into a point within the configuration space. Is a union of two contractible guys, right? Which means the assumptions are satisfied. And now it says whenever you have something within this space which is not categorical, for example, this circle or this circle, or of course even some bigger subspaces, there must be at least one position here which cannot be, I mean, which is a point of discontinuity, a point of instability if you want to travel to this position in the workspace. Okay, so this gives you an entire subspace of discontinuities, and in fact, if you consider the dimension of this okay, let me return. I'm sorry. Let me return back. So this means that if you have a categorical fiber, then on each non-categorical fiber there is at least one point. So you get something which is generically of codimension m minus n. So for example, if you have redundancy 1, then you have a subspace which locally separates this set of all tasks, of all queries. So it's quite big. This was kind of a surprise for me. And then there are some standard results. For example, the topological complexity of singularity-free motion planning is always at least the Lustenich-neural category of the workspace. It's also almost at least the number of minimal number of continuous sections for the forward kinematic map. Then again, if there is some categorical fiber, then the topological complexity is at least the category of C. So in general, you expect that the category of C is bigger than the category of W, which means that under this assumption, you get a better estimate than it's here. And then one important case, as I said, parallel mechanisms often have inverse kinematics. If this is the case, then the topological complexity of singularity-free motion planning is between the topological complexity of the workspace and the topological complexity of the configuration, singularity-free configuration space. So SF is missing. Okay, so these are just some sample theorems. I have other results, but they are more technical. And anyway, this is still some work in progress. Fine. So I think I'm just in time. This is the conclusion of my talk. So thank you for your attention. And of course, are there any questions?
So thank you very much, Peter, for this very, very nice and very interesting talk. So I would like to ask you all if you have any questions. Nevertheless, I do have a question. So for this really, really simple example that you had, so what is the topological complexity of the singularity-free part?
It is free. So I mean, you can do it with free motion plans. And so in many cases, you can, I mean, the theory essentially gives you specific motion plans. So I can describe them, but I mean, it's complicated. I can write the corresponding formula, so that would be, formula. It's not actually formula. It's kind of a rule. How do you move in each of those subspaces?
So actually have you could come up with an algorithm for
yes. I mean, in this simple case, I'm not claiming about the general. Okay, so as you know, in topological complexity, lower bounds are kind of come from cohomology and are not constructive. Upper bounds, so explicit motion plans, are usually kind of constructive. So, I mean, yes, when you have an upper bound, usually you have a set of rules. Yeah.
And then typically...
maybe it's not optimal, but you can do that.
But then typically you would probably have more than one solution to your problem, like given two points, there should be several motions, possible paths from one position to the other. So do you have any idea about how to, in the end, give a practical, recipe, which one to choose out of all these? Any kind of criterion or measure or something which would, tell somebody who is actually a mechanic how to get about choosing the right path?
I mean, as I said, okay, if you are not concerned whether you are not really optimal, so instead of having 5 rules, which is maybe optimal, you make 8 or something, then usually you can obtain some motion plans. It is true, and this is something that I discussed in some previous talks, is that what we consider as one motion plan is usually defined on a disconnected domain. So from the programming viewpoint, it could be considered as several different plans. I mean, you know, you can define something which is continuous on a subspace which has like 5 components, right? But if you do the programming, then you need essentially to a program which checks within which component it is, and then does the programming of the motion. Now, as I said, it is one domain of continuity, but I believe that from the programming viewpoint, these are like 5 rules. You understand the point? So it's really the question: what exactly are we computing in this? But yes, so I mean, if you just look at domains of continuity, then it is relatively I won't say easy, but possible to describe explicit roles. Yeah.
Any more questions? It seems that not, but I still have one more.
Okay.
Maybe it's trivial or maybe it's silly. But you started by saying that this problem, motion planning, is sometimes called the piano movers problem. Have you thought about this configuration space of moving a piano from one point in a room to another point? Of course, I understand.
I mean, this is way older than is not only than my interest in this, but that me. I mean, this is something that was kind of explicit in the. I mean, if you look at the literature from the 50s and 60s, 1950s and 1960s, you can find this because with the piano mover problem, there is another layer. It's not just a point. Right, it's some geometric object, and but there is some interesting geometry. So you have something which is of irregular shape, and you move this around, and yes, there is some not old, ancient literature which discusses this problem. I didn't add anything to this.
As I said, probably it was a silly question, so thanks anyway.
No, I know that you have a big piano, and you know exactly what is what is a practical problem to move it in a small room. But I don't know what's the topological complexity of moving your grand piano in your small room.
Well, maybe not topological, but complexity by itself is quite high. So thanks very much. And if there are no more talks, I would like to thank Petar for this really, really nice talk, and thank everybody else for coming and paying attention to this interesting topic.
Thank you.
Okay, thank you.